What was I talking about?
The distance.
Python code.
Distance of t between two poles.
Right, it has distance 3. I was talking about why it's perfect. Yeah, okay. So, right, so perfect means that this is the smallest code that has distance 3. How do I argue that this is the smallest code? That's what I want to talk about. So, like here, for example, let's go back to this one. In the repetition code, how do you know what error you have? Well, the repetition code, this 313 code, the parity checks are just like 0, 1, 1 and 1, 1, 0, right? So the first parity check checks the parity of the second of bits 2 and 3, and the first, and then here. The first parity check measures the parity of bits 1 and 2, and the second parity check measures the parity of bits 2 and 3. And if you understand, if you measure both of these parities, that tells you where the error is, and so you can correct it. For example, here you'd measure the parity odd, so therefore you know the error is on the second qubit. The same thing is true here. You should be able to measure these stabilizers and locate the error. So for example, copy paste. I give up. For example, what do you do when copy paste doesn't work? I guess you just write it out. All right. Right. So I want to be able to locate the error based on based on these parities. So each of these is a stabilizer. So its eigenvalues are plus minus 1. And so so you measure the stabilizer, you get either plus 1 or minus 1. That should be enough to tell you where the error is. So let me show you how that works. If you have an error on qubit 1, so the error is ZIII, then that anti-commutes with this. So the syndrome is going to be, the parity is going to be minus 1 if you measure it. It commutes with that, so you get plus 1. Anti-commutes, commutes. So you end up with minus, plus, minus, minus. Or maybe it's easier just to say 1, 0, 1, 0. So 1 means minus 1 and 0 means plus 1, just so it's binary. Right. So then, and then the same is with any error. So that's with this error. If you have a different error, you get a different syndrome. So for example, if you have I, Z, I, that'll give you that commutes, anti-commutes, commutes, anti-commutes, like that. And okay, and so so the idea is you have one of let's see, there's 16 possible errors that you could have. So this is just 2 of them, but the other ones are the all identity string, that's 1, and then there's 3 poly errors on qubit 1, 3 errors on each qubit. So 1 plus 3 times 5. That's 16 possible errors of weight less than or equal to 1. And the claim is that all 16 of those errors will give you a distinct string here, meaning that you can exactly identify what it is. A distinct syndrome here, which means you can exactly identify what it is. And it's perfect because we can't go any smaller, because 16 is equal to 2 to the 4. There's only 4 syndrome bits, there's only 4 parity checks. And so you can only have 16, 2 to the 4 different parities, and that's exactly enough to identify and locate the error. So it can't be any smaller. Like this code is not perfect because well, a couple of reasons, but here you have 8 parities, so there's 2 to the 8th, 256 different possibilities for the syndrome string. But the number of errors is just 1 plus 9 times 3, which is 28. So 28 is much less than 256, and so this is definitely not a perfect code. But this 513 code is perfect. You can make it smaller. Actually, so that same logic works for higher distance, although we don't care, probably. What's interesting? I guess, yeah.
For higher distances, it would just be combinations of weight two arrows or weight two faults.
Yeah, exactly. So perfect for distance d means you said t is equal to d minus 1 over 2. So if d equals 3, t is equal to 1. If d equals 5, t is equal to 2. Yeah, and then what you want is you want 1 plus n choose 1 times 3 plus n choose 2 times 3 squared plus n choose t 3 to the t. This is the number of errors of weight less than or equal to t. And so if the code's perfect, this will equal 2 to the number of stabilizer generators. But even if the code's not perfect, in general, like you'll have less than or equal to, because you got to have at least as many stabilizers to be able to identify which of these errors you have. Usually. So there's a small technicality there that I'll talk about in a moment. Let's see. Other things is, yeah, so perfect also has to do with the fact that it's a qubit. So if I had a higher dimensional system, the notion of perfect and stuff would be different. So for example, if you have a Q-trit code, so Q-trit code means that each system is a 3-dimensional system instead of a 2-dimensional system. All the stabilizer algebra still works. You just define X to be, right? You just define X to be like this matrix. And you define Z to be this matrix. And all stabilizer algebra, the Gauss-Canel theorem, all that stuff still works with Q-trits. But now let's see. So the notation is going to be N, K, D, and then I'll put a 3 here to indicate that the size of the system is 3 instead of 2. So if you don't see a subscript, it means it's qubits. If you see a subscript, then it's some higher dimensional system. And in this case, let's look at what this says. So it'll be 1 plus n choose 1 times, all right, so it's not 3 anymore because 3 was the number of 1 qubit non-identity 1 qubit poly operators. Here, the 1 qubit poly operators are I, X, X squared, I, Z squared. Yeah, so different combinations of X and Z, where X cubed is equal to 1 and Z cubed is equal to 1. So I guess there are 8 non-identity 1 qubit 1 Q-trace poly operators. Because the power of X could be anything up to 3, the power of Z could be anything up to 3, or up to 2, 3 minus 1. Yeah, so it's instead of, so it's like that, so you have an 8 there instead of a 3. Right. 3 squared minus 1 instead of 2 squared minus 1. And yeah, so if t is equal to 1, then this, we want this to equal 3 to the number of stabilizer generators for perfection, or less than or equal in general. But there is, for example, there is a 313, I think, yeah, 3133 code. This is possible because 1 plus 3 choose 1 times, wait, no, that's not possible. Wait. 1 plus 3 times 1 plus 3 times 8 is 25, right? Which is more. So it's not even a power of 3, so it's definitely not perfect. All right, so good. It doesn't make sense. But I think I can find it. Let's see.